Hey there guys, Paul here from the engineeringmindset.com. In this video, we're going to be discussing electrical current. We'll be looking at what is current, the different types of current, how to check the ratings of your electrical devices, as well as how we use safety features to save you from being electrocuted. Current is the flow of electrons in a circuit. To use electricity, we need electrons to flow in the same direction around a circuit. We usually use copper cables to form the circuit because the atoms that make copper have a loosely bound electron in their outermost or valence shell, which is free to move around inside the metal. This free electron is very easy to move, which is why copper is so popular. It's so easy to move that it will naturally just move to other copper atoms by itself, but this occurs randomly in any and all directions, which isn't useful for us. For us to make use of this, we need lots of electrons to flow in the same direction along the circuit. We can then place things like lamps in the way of these electrons so that they flow through it and then they generate light and heat, etc. To do this, we need to force the electrons to move, and we can do that by applying a voltage. Voltage is the pushing force. It's like pressure in a water pipe. The more pressure we have, the more water can flow. The more voltage we have, the more electrons can flow. We've covered the basics of voltage in detail in our previous video. Do check that out, links in the video description down below. So we need a lot of electrons to flow along a circuit and through our lamps to get them to shine brightly. However, the cable and lamps can only handle a certain amount of electrons passing through them. Just like a pipe is rated to handle a certain amount of water passing through it, or a certain pressure. If it exceeds this, then the pipe will burst. Likewise, if too many electrons pass through the cable or the lamp, then they will just burst or burn out. We refer to the flow of electrons as current, and we measure this in the unit of amperes, although you'll usually just hear people say amps. This is represented with a capital A. For example, this fuse has a 3 and a capital A, which means it's rated to 3 amps of current. We'll look at how we use fuses later on in this video. If you look on the plugs of your electrical devices, you should find labels from the manufacturers which tell you what the product is designed to handle. For example, this laptop charger tells us that for the device to work, it needs an input of between 100 and 240 volts and 1.5 amps of AC or alternating current. The charger will then convert this to give an output of 19.5 volts and 3.3 amps of DC or direct current. AC and DC are different types of electricity. The plugs in your homes will provide AC or alternating current. In this type, the electrons do not flow in a continuous loop, they instead alternate between moving backwards and forwards, just like the tide of the sea. Your electrical devices like laptops and mobile phones will use DC electricity or direct current. In this type, the electrons do flow in only one direction, much like the flow of water in a river. We transport electricity from the power stations in AC alternating current and send this to our cities and homes. We use AC here because it can be transported very efficiently and over much greater distances than if we were to use DC direct current. We can also very easily increase or decrease the voltage using simple transformers. We've covered how transformers work in our previous videos, links down below for that, do check them out. We mostly use DC direct current in the circuit boards of small electronic devices like laptops, mobile phones and televisions. That's because DC is easier to control and allows circuits to be smaller and more compact. Many appliances will use a combination of AC and DC. For example, a washing machine will use AC for the induction motor, which is used to spin the tub with the clothes in. But the circuit board, which controls the settings, the lights, the timers, as well as how fast the motor spins, will use DC power. We can convert AC to DC using an inverter. This is extremely common in electronics. We've covered how inverters work previously, links down below if you want to watch and learn about that also. People often refer to a river or the tide of a sea as having a strong current. It's very similar to electricity. A river with a lot of fast-flowing water is said to have a strong current. The same with electricity. A cable with a lot of electrons flowing through it has a high current. A river is able to handle a certain amount of water flowing through it. But if more water enters than the river can handle, then the river will burst its banks. The same with electricity, the cable will burst and burn out. Therefore, manufacturers need to be able to test cables and lamps to find out how much current they can handle. We also want to be able to see how much current is flowing through our circuits, as well as being able to calculate this. We can measure this using an ammeter, and we measure the flow of current in the circuit using the units of amps. So what is an amp? 1 amp is equal to 1 coulomb, and 1 coulomb is equal to approximately 6,242 quadrillion electrons per second. What does that mean? Another way to look at this is that to power this 1.5 watt lamp with a 1.5 volt battery, approximately 6,242 quadrillion electrons need to flow from the battery and through the lamp every second for the lamp to stay on. If we reduce the voltage, then less electrons will move and the lamp will become dimmer. If we increase the voltage, then more electrons will flow and eventually the lamp will not be able to cope, so it will burst or burn out. So to measure the current in a circuit, we need to connect an ammeter in series so that the current flows through it. Think of it like a water meter. The water needs to flow through the water meter for us to know how much water is flowing in the pipe. Likewise, we need the electrons to flow through our ammeter so that we know how much electricity is flowing in our circuit. Instead of using an ammeter, we're going to use a multimeter, as we can do a lot more with this device. I'll leave some links down in the video description where you can pick up a good multimeter cheaply. I highly encourage you to get one of these for your toolkit. They're pretty cheap and are very useful. If we connect a lamp to a battery in series, then we can measure the current using a multimeter by connecting it in series. If we connect this 1.5 volt battery and this lamp, which has a resistance of 1 ohm, then we get a current reading of 1.5 amps, which means 9,636 quadrillion electrons are flowing through the lamp every second. Because it's in series, all the electrons in the circuit are flowing along the same path. So that means we can move the multimeter to here and we get the same reading. If we add another lamp to the circuit, connected again in series, the lamp also has a resistance of 1 ohm, then we are adding more resistance to the circuit, so the electrons are slowed down. In this case, we get a reading of 0.75 amps, which means 4,818 quadrillion electrons are flowing per second. This is in series, so again, we can move the multimeter and we get the same reading. If we now connect the circuit with 2 lamps in parallel, both with a resistance of 1 ohm, and connect this to a battery of 1.5 volts, then in the main wire, to and from the battery, we get 3 amps. But on the branch of each lamp, we get 1.5 amps. That's because the path of the electrons has split, so the electrons are shared with some flowing through lamp A and some flowing through lamp B. In this example, both lamps have an equal resistance, so the current is split equally. But if the lamps are of different resistance, then the current is split unequally. For example, if lamp A has a resistance of 1 ohm and lamp B has a resistance of 3 ohms, then in the main wire we get an amp reading of 2 amps. In the branch for lamp A, we get 1.5 amps, and in the branch for lamp B, we get 0.5 amps. As you can see, lamp B is dimmer because there is a higher resistance, so less electrons can flow through it. In both cases, the amps in the branches will add up and are equal to the total current flowing in the main wire to and from the battery. Now I mentioned that lamp B was dimmer because the resistance was higher. If you remember, I also said that cables and lamps etc. are only rated to handle a certain amount of current. If it exceeds this, then they can burn out. So to restrict the amount of current that can flow, we can add resistors into the circuit or into part of the circuit. These act like speed bumps and slow the electrons down. Resistors are like putting a bend into a garden hose. The kink adds resistance to the flow of water, which reduces the amount of water that can flow out of the hose. Similarly, we can add resistors to the circuit and it slows down the electrons. For example, this LED is rated at 25 milliamps and 3.3 volts, but our battery is rated at 9 volts. So if we were to connect the LED to the battery, it will just burn out because it can't handle that much voltage and current. So to stop the battery from burning out, we need to place a resistor into the circuit. In this case, we'll use a 270 ohm resistor to bring the voltage and current down to a safe level for the LED. If you want to see how much current is flowing through your electrical devices at home, then you can use one of these cheap energy meters. You simply plug your appliances into it and it'll measure the voltage, amps, watts, power factor, etc. and you can then even calculate how much it costs to use the appliance. I recommend you have one of these. They're a great little device for your toolkit. I'll leave some links down below for where you can get a good one very cheaply. So we saw earlier that we can use resistors to reduce the amount of current flowing in the circuit and protect our devices. Another thing we can use is a fuse. Fuses, in a basic sense, have a thin piece of wire inside them which is rated to handle a certain amount of current flowing through them. In this case, this one is rated to handle 3 amp or 19 quintillion 272 quadrillion electrons per second. The fuse acts as a weak point and is very cheap to replace. So if too much current flows in the circuit, it will burn out and open to break the circuit and protect the more expensive electrical components. You can find these mounted on circuit boards, and you can also find these built into some plugs. For example, this plug from the UK has a fuse built into it to protect the electrical device. Another device we use, and you've probably seen these in your homes, this is the circuit breaker. It's essentially a switch that will automatically open to break the circuit if it detects too much current or too many electrons flowing through it. It's rated to handle a certain amount of electrons flowing through it per second, but it measures this using heat or an electromagnetic field to detect and act on if too many electrons are passing through it. If it exceeds this, then it will open to break the circuit. If, for example, we slowly add load to a circuit, then the bimetallic plate will detect this slow rising current because the current causes it to heat up. As it approaches the design rating, it will break the circuit to cut the power and protect the cables and devices. The load can then be reduced and the circuit breaker reset, unlike a fuse. Another extremely important function is if, for example, you touch a live component and receive an electrical shock. There will be a sudden surge in current and the circuit breaker can detect this and cut the power almost instantly to stop you being electrocuted and save your life. Okay, that's it for this video, but if you want to continue learning about electricity and electrical engineering, then just click one of these videos on screen now and I'll catch you there for the next lesson. If you have any questions, then let me know in the comment section down below.